Okay, here's the first one from the strategy choices. So you look at this and you're not really sure at first if this is integration by parts or U-substitution. If this was some squared, like 2x squared, 5x squared, then this x would work really well with that. And then we'd have a U-substitution. We'd make this u and then this would roll in to being the du. We'd like that. But since this is linear and this is linear, this is an integration by parts. So you want to notice that this is u and then this is dv. And remember that the integration by parts formula says that u dv can be rewritten as uv minus the integral of v du. And our hope is that we take an integral that we can't do and we rewrite it as this integral, and then we can do that integral. So over here, let's say that u is equal to 3x, dv is equal to e to the 2x dx, then du is equal to 3 dx, v is 1/2 e to the 2x, and then let's make that substitution. So the original integral then can be rewritten as uv, so that's 3/2 x e to the 2x minus the integral of v du, which is 3/2 e to the 2x dx. The first part we just rewrite because it's already finished, and then we do the integral. And the integral is just 3/4 e to the 2x. And again, how do I get the 3/4? I'm taking the integral of e to the 2x, and the reverse chain rule or u substitution tells me that I create another factor of 2 in the denominator, making that 3/4 plus c. I actually could have used tabular if I wanted to. Remember, tabular says go ahead and put your u there and your dv there. Take derivatives here. Take antiderivatives on this side. Match them up with the diagonals, and then put plus and a minus, and then go ahead and match them up. 3x times 1/2 e to the 2x gives us this term, minus 3/4 e to the 2x gives us this term. So this idea is organized, and we just call that tabular, but it's just integration by parts. And remember, integration by parts is essentially the product rule, and we derive that from the product rule itself. The second one is secant squared tangent. So when you look at this, this is like a trig integral, and it's kind of nice because if we think tangent is u, then du is secant squared, and this integral immediately turns into u du. That integral is just the power rule, so it's u squared over 2 plus c, and remember u is tangent, so we get tangent squared over 2 plus c, and we're done. We didn't have to rip off anything. We didn't have to change any secants to tangents. We had du and we had u sitting right there, and so it made it pretty easy. The third one, you look at this and you're like, well, I have a quadratic and I have a constant. This can't factor. Ooh, and this is a square, so it's likely inverse tangent. And remember, eventually we need to know that the basic rule says that if I can get an integral to look like this, the integral of du over u squared plus 1, I know that that will be inverse tangent of u. And so we need to manipulate this algebraically to make it look like this. So we're going to factor out a 4 in the denominator. So it'll look like 1/4 x squared plus 1 dx. So we got the plus 1 that we wanted. And now we need the u squared. So we need to write this as something squared. I also am just going to take that 2, I might as well factor it out. And I could have simplified it to 1/2, but let's just leave it as 2/4 for a second. And so I have dx, and instead of 1/4 x squared, I'm going to write it as x over 2 squared plus 1. Now I'm getting really close. I have a u squared plus 1, but I have dx instead of a du. So if you think about it, u is x over 2, which means that du is dx over 2, which means that 2 du is equal to dx. And now I can make the full substitution. So 2/4 the integral, and instead of dx, I'm going to write 2 du. So 2 du over u squared plus 1. And in this particular case, we get 2 times 2 over 4. And all of those just cancel. It doesn't matter if it didn't cancel. If this was like 5 over 7, it would just be 5/7. But what we have is the integral we know. And we get inverse tangent of u, but u is x over 2 plus c. Okay, that's the third one. The fourth one, you look at this, you're like, oh my, this is sine times an exponential. Can't really do much with this except Well, we can do integration by parts. We just have to do it twice, and we called this the do without doing method. Okay, and you'd have to go through the whole long process of doing integration by parts twice. What we did decide, though, in class, that if you really understand tabular, you actually can use tabular to do this. Remember, on this side, we're taking derivatives, creating a factor of 4. Over here, I'm taking antiderivatives, dividing by 2. Taking the derivative of cosine, I'm going to get a negative sign. And I get a 1/4 because I get another factor here. And we do our this where we get plus, minus. And then this is kind of the hard part of how to use tabular to do these. These two together make up that last integral. And so we would have wrote it as a u and a v. So 1/2 sine of 4x e to the 2x. And then the next uv, the 4 and the 4 cancel, so it's just a minus cosine 4x e to the 2x. And then this is that fraction. We would have gotten a minus 1/4 the integral, and we would have had to add that to the other side, making this a 5/4. But so 5/4 of this integral equals this. Well, I can just divide by 5/4 and get rid of that, and then I've evaluated the integral. The integral is equal to this without actually doing the integral. Just as a reminder, I did tell you in class that this type, the do without doing integral, will not be on the test. You should be able to do it. Maybe it's a bonus question, but it's not on the test. Okay, number 5. Number 5 is the easiest one. You look at it and you're like, ooh, I can factor the denominator. Maybe it's partial fractions. Maybe I can separate it to x plus 2 and x minus 2. But when you look at it, the 5x in the numerator can easily be manipulated. If you just let u equal x squared minus 4, you can get du to be 2x dx. And so this, remember, that 5 can just be factored out. And then what we want to do is we would love that to be a 2x dx. And that to be a u. And if we just put in a 2 over here, this then really is just du, and the whole thing turns out to be just 5/2 integral of du over u, which is just 5/2 natural log of u, where u was x squared minus 4. And then you're done. Realistically, you could have done it at the very beginning. You could have just said, bring that 5 out, put in a 2, and then again, noticed right away that this is just du over u, and then go from there. Again, however you want to manipulate it, whether you have the vision to see that you needed the 2, so you had to put in the 2, whatever you do want to do with the 5, factor it out, leave it in, it doesn't really matter. Eventually, this linear function worked really nice with this quadratic and gave us the natural log. Okay, starting with number 6. You see tangent, and we don't really know what the integral of tangent is. It's maybe a rule you've memorized to this point, but really, this is just some algebra at the beginning. What we're going to do is we're going to rewrite tangent as sine over cosine. And then we take a step back and we're like, okay, what are we going to do from here? Well, if you made this u, then this would be a du in the denominator. Well, we can't have du in the denominator. We need something times du. So it does make more sense to treat cosine as u. But if cosine is u, we would love then to have a negative sign x dx. But realistically, we do. We just have a negative sign. So this whole thing turns into just negative integral of du over u. But we know what that is. That's just negative natural log of u. But u, oops, that was supposed to be an x. Cosine x plus c, and you're done. Now, that is just the integral of tangent. So if you had an integral of tangent, that is just the rule you need to know. But realistically, you're going to know the process to do it, which is just a U-substitution rather than anything else. Okay, similar, that you don't know the integral of the natural log unless you have it memorized. But again, if I make this natural log of 4x or natural log of x squared, does that throw you off? This is integration by parts. And the interesting thing here is that this is our u and dx is our dv. I know it doesn't look like two functions, but it really is. And so go ahead and make u the natural log of x. dv is just dx, which makes du 1 over x dx. It makes v, just the integral of 1, is just x, and then rewrite it. And again, integration by parts says that the integral of u dv equals uv minus the integral of v du. So this integral is going to equal uv, so x, natural log of x, minus the integral of v du. But when you take v times du, x over x just gets rid of, and that's just 1, and then the integral of 1 is just x. So then the whole answer is just x ln x minus x plus c. And again, if that's an integral you want to kind of remember, or at least be comfortable with, that's fine, but integration by parts shows us that. All right, here we get cosine squared. If we had a sign in there, we could rip off the sign and treat that as du, and then this would be like u squared. We don't have a sign, so there's no way this will work. This is one of the worst ones because the only way to do this integral is to know a trig identity. And that trig identity actually doesn't do the integral for us. It just gives us the ability to take cosine squared and write it as 1/2 plus 1/2 cosine 2x. The nice part is this integral we can do. The integral of 1/2 is just 1/2 x. The integral of cosine 2x is just plus 1/4 sine of 2x. And again, the fourth comes from the fact that I have a 2 here. When I integrate, I have reverse chain rule implications, and it goes from 1/2 to 1/4 plus c. And we're done. Again, this is a trig identity that cosine squared equals 1/2 plus 1/2 cosine 2x. So rewrite it using the trig identity, and then integrate the new thing. The new thing being easily integrated just by trig rules and power rule. Number 9, when you look at number 9, you're like, okay, this is a quadratic, and this is a line. Maybe I can do U-substitution. But that pesky little 2 makes it so it's not going to work. If the 2 wasn't there, then it would be just fine. We could manipulate the 7x to make it match the 2x. But that 2 makes this a integration using partial fractions. See how the denominator can factor? So what we're going to do is we're going to say 7x plus 2 over x minus 3 times x plus 3. And I can rewrite that as sum a over x minus 3 plus sum b over x plus 3. We're going to multiply by the common denominator, which just gets rid of all the denominators. And gives us a times x plus 3 plus b times x minus 3. And now I'm going to say, well, you know what? This needs to be true for all x values. So again, this is equal to this because this is equal to this for all x. So why not just pick the easiest x values? What if x was 3? If x was 3, this would make this, what, 21 plus 2 is 23. It would make, oh, we'd make that 0, and it'd make that 6a. And so a is equal to 23 over 6. Not the nicest term, but that's what a is. If x is negative 3, then this would be negative 21, so negative 19 equals, that term would go away, and we'd get negative 6b. So b is equal to 19 over 6. And so when you go back to this original thing, we know that this integral then is equal to the integral of a, 23 over 6, all over x minus 3 plus 19/6 over x plus 3, all with a dx. And again, those numbers mean nothing, right? They can each be factored out. If that was a 4, if that was a 10, it doesn't matter. They can just be factored out. And realistically, we're just integrating dx over x minus 3 and dx over x plus 3, and those are just logarithm rules. So then the answer is going to be 23 over 6 natural log of x minus 3 plus 19/6 natural log of x plus 3 plus c. It's likely that on the test I make it so a and b work out to nice values. I probably just wrote this question really quick and just was thinking more like you guys recognizing what type it is rather than making sure that it actually worked out right. So don't worry about it. They don't have to be whole integer values. They ended up being fractions in this case. And number 10, we look at it like, oh, this is that classic form that we're going to need to draw the triangles. If there was an x next to the 5, well, then we could do U-substitution, but there's not an x. And so we have to draw a triangle. So we draw our triangle and then prepare to do a trig substitution. So that's theta. See how this is x squared plus 4? So we know that this, the square root, has to be the hypotenuse. So So that's x squared plus 4. I'm going to make that x and that 2. That way my x is always in the numerator, because when I do tangent, it's going to be opposite over adjacent. And so we do tangent of theta is x over 2, which means that 2 tangent equals x, and I can take a differential of that and get 2 secant squared theta d theta is equal to dx. And then I have to do that secant. Secant of theta is equal to the square root of x squared plus 4 over 2, right? Secant is hypotenuse over adjacent, and that means that 2 secant theta is equal to the square root of x squared plus 4. And now I can make the substitution. This whole integral then equals, I'm just going to pull that 5 out in front. I have the dx, which is right here. So 2 secant squared theta d theta, I substitute in for dx, and then the square root is right here. 2 secant theta. Okay, those 2 cancel. That power of secant cancels, and so realistically I have 5 times the integral of secant theta d theta. Now that is an integral I showed you how to do in class. I said that, well, unfortunately, it's kind of this weird rule that if you wanted to do this, you could multiply top and bottom by something, and that something ended up being secant plus tangent. And when you do that, you end up getting the integral of secant squared plus secant tangent all over secant plus tangent. And the nice thing, the reason we did that is because this is u, and there's its du. This is a u, and there's its du. So realistically, if this is u, du is right there. And all of this turns into du over u, which we then know as the natural log of u, but u is this. And so what I just did was proved to you that the integral of secant theta is the natural log of secant plus tangent. Okay? And so what happens here is I need to put this up here. So this is 5 natural log of secant theta plus tangent theta plus c. But again, I can't have thetas in my integrals. I created this construct to be able to do the integral. I need to have eventually back with x's. But again, if you don't know what secant theta is, go to the triangle. What is secant theta? Secant theta is hypotenuse over adjacent. So this is secant. And then what's tangent? Well, tangent theta is just x over 2. So then I replace that. So I get 5 natural log of, I have to move this just a little bit so you can see, secant theta, which was the square root of x squared plus 4 all over 2 plus tangent theta, which is just x over 2 plus c. And we're done. Okay, so working on number 11, you look at the integral of the natural log over x. Like, oh man, I don't really know what to do, but really, if this is just u, that's du. Remember, the derivative of the natural log is 1 over x. And so that whole thing is really just that. And again, that's just u squared over 2 plus c. And so that's just the natural log of x squared over 2 plus c. Again, I know that might take a second to look at, but really you have u and du already right there. Same thing here. There's your u. Du, meaning the cosine. We don't even have to rip it off. There is a cosine nice sitting right there already. This is really already just u squared du. Now, if it was like cosine cubed, we'd have to rip off a cosine and turn the remaining even cosines back into sines using cosine squared plus sine squared is equal to 1, but there's just one cosine and there's a bunch of sines, so we can do this. We get u cubed over 3 plus c, which is just sine cubed over 3 plus c. And again, if you take the derivative of this, you'd bring the 3 down. The 3's would cancel. You'd decrease the power by 1, and you'd multiply by the derivative of the inside and create that cosine. Really, remember, U-substitution is just reverse chain rule. 13, you look at this and see how the denominator is one term. It's not like x cubed plus something or minus something. It's just x cubed. That does allow us to split this up. And so we can view this as x over x cubed plus 3 over x cubed. Okay, we can simplify this a little bit because x over x cubed is just 1 over x squared plus 3 over x cubed. But that's easy, that's just power rule. Increase the power by 1, dividing by the new power. Increasing the power to make it a negative 1 power, and dividing by it makes this negative 1 over x. Increase the power by 1, divided by the new power, makes this negative 3 over 2x squared. And again, feel free to take the derivative of those terms. You will get back the original function. Down here, you might think this looks like integration by parts because it looks like a function times a function, but if you look closely, this is cosine of x squared. If x squared is u, this x is great. It makes us work with it. So realistically, we would love for that to be a 2x because then it's du, and if I put in a 2, I have to put in a half because I can't change the value of the function. Okay? So what happens here is that this whole thing just becomes 1/2 cosine u du. The integral of cosine is just sine, so I integrate sine to get sine of u, where u was x squared. Again, take a derivative if you want. Take the derivative of this and make sure you actually get back x cosine x squared. The derivative of sine x squared would be cosine x squared times 2x. The 2 and the 2 would cancel and left with no coefficient. Okay?
What?
So what we have here is the natural log of x cubed. It's very similar. If we use the property of a logarithm, what we can do is we can actually bring that 3 down and write it like this. We can bring the 3 outside the integral. And now this is exactly the integral we did on number 7. So look back on number 7's video, and this is integration by parts, but we know that this is just x ln x minus x plus c. Again, using properties of logarithms, they just pop up. The property of a logarithm is that log of, x to the n can come down in front. And the last one, again, this might look like integration by parts, but it's not. This is x cubed and this is x squared. They play really nice together. Again, you want to make u x cubed, which makes du 3x squared dx. And you want this to be a 3, so just leave the 3, factor out a 5. So that's going to be 5 times 3x squared ex cubed dx. That really just turns into 5 times the integral of e to the u. And then the 3x squared dx makes du. Piece of cake. So that's just 5 times the integral of e to the u is just e to the u. And u was x cubed. And you're done. Okay, here's number 17. You look at number 17, and this is probably like the basic integration by parts because it's a function times a function. It's not cosine of x squared. There's no way u substitution is really going to work here. And so we'd say u is equal to x, dv is equal to cosine x dx, which makes du dx, which makes v sine x. And remember, integration by parts says that the original integral is some u dv, and that's going to be rewritten as uv minus the integral of v du. Okay, so we're going to take this integral and rewrite it as uv x sine x minus the integral of v du. And again, we manipulated it so we can do this integral. This integral we know, the integral of sine is negative cosine. So then this is just x sine x, integral is negative cosine, the negatives cancel and give you plus cosine x plus c. We could do this tabular if we wanted to. I'm a pretty big fan of tabular. We could do that, and we just take derivatives and take antiderivatives. Plus, minus, x times sine x. 1 times negative cosine gives us positive cosine. Boom. Same thing. Again, tabular probably has less room for error than the original ones, but just got to remember that derivatives on this side, antiderivatives on this side, and then the whole plus minus, plus minus. And again, just because this is plus minus every time doesn't mean that your answer goes plus minus, because individually the terms themselves can be negative, which again caused this one to actually be positive. So that's 17. 18 is a pretty hard one because you're not really sure what to do at first, but you're taking cosine of something, and that something ends up being the square root of x. It's likely then that you make that u, which then makes du 1 over 2 square root of x dx, which says that then I can multiply on both sides to do this, and then I can notice, well, the square root of x is really just u. So really then, 2u du is equal to dx. And I can go in here and make some substitutions. This says cosine of the square root of x, but that's just cosine of u. And then dx is 2u du. And so I've rewritten this integral. I'm going to pull that 2 out in front. Is u cosine of u du. Well, it might not look like it helped, but it did. This is a difficult integral. This integral we actually just got done doing on number 17. Number 17 is the exact integral. This is integration by parts. Again, this is some u and some cosine u. We can take derivatives on this side, antiderivatives on this side. We can match those up. And so I can say equals to 2 times u sine u plus cosine u. And u is the square root of x. And so I get 2 square root of x sine of the square root of x. And I'll go ahead and distribute the 2 to this one as well. 2 cosine of the square root of x plus c. 19, we got sine to the 4th cosine cubed. You notice cosine is odd right here, which means if I rip off a cosine, I have an even number of cosines left. That's probably the key step. Because if I leave a cosine squared, ripping off cosine over here, this is my future du. And all I have left to do is to change that cosine into a sine. But I can just use the Pythagorean theorem identities to say that cosine squared is just 1 minus sine squared. Leave the cosine x dx alone over here. And then realistically, this is just u to the 4th times 1 minus u squared, and that's du. So then this is u to the 4th minus u to the 6th. And now I have just an easy power rule. That's just u to the 5th over 5 minus u to the 7th over 7 plus c. Then u was sine x. Remember, the whole point was that we made u sine x, and we ripped off a cosine, because if u is sine x, then du is cosine x dx, and so then our answer should be sine to the 5th over 5 minus sine to the 7th over 7 plus c. Okay? And last, number 20. Number 20, it's a little tricky because it might look like it's one of our trig substitutions where we need the triangle. It's actually not. See this x here? If we make this u, if u equals 1 minus 4x squared, then du is equal to negative 8x dx. If we want that to be a negative 8, all we have to do is multiply by negative 4. And again, if we multiply by negative 4, we have to multiply outside by negative 1/4. And we get negative 1/4 the integral of du over the square root of u. This is just power. We got to think of this as u to the negative 1/2. If you can't see that, maybe you should write it like that before doing the integral. Because I'm going to increase the power by 1. Increase the power by 1 to make it a half. And then dividing by half is the same thing as multiplying by 2. So then this is negative 1/2 u to the half, where u was 1 minus 4x squared to the half power. And so the whole answer should be negative square root of 1 minus 4x squared all over 2 plus some c. If you did it the other way, you're going to get the same answer. You're probably just going to have to do a decent amount of work to get there. And so we would draw the triangle. That would be theta. This is the hypotenuse because it's 1 minus. This is like a c squared minus a b squared. So this would be 1, this would be 2x, and this would be the square root of 1 minus 4x squared. Okay, we would have to do in sine, so sine theta would be equal to 2x over 1. Over 1 is not really anything. And then we could do cosine theta would equal the square root of 1 minus 4x squared. If sine theta is equal to 2x, that means that cosine theta d theta is equal to 2 dx. Okay? And so then replacing all of this, see how this is a 2x and this is a 2x, which literally means that sine of theta is equal to 2x. I can just plug that in. So that's that. dx, so I have to divide by 2. So that means that dx is cosine theta d theta over 2 all over the square root, but the square root is just cosine. Okay, the cosines cancel, and I'm left with 1/2 the integral of sine theta d theta. That integral is just negative cosine. Sorry, I'm going to have to go up here. That's just 1/2 negative cosine theta plus c. And if you look at what cosine theta is, go to your triangle. Cosine of theta is this over this, and it's the exact same thing. So either way, whether you do a trig substitution and have to draw the triangle, or you actually just notice this is u sub, it's the same thing.